What would it take to finally prove that life once stirred on Mars? A fossil? A molecule? A pattern in stone that looks too deliberate to ignore? In Jezero Crater, NASA's Perseverance rover may have stumbled on the closest thing yet. Mudstones etched with sharp chemical fronts, dotted with nodules, and rich in minerals that, on Earth, often whisper of microbial life. The evidence is compelling, but is it life or just chemistry, playing tricks again? Jezero is a crater about 45 kilometers wide, cut into the Syrtis Major highlands. Long before Perseverance ever touched down, orbiters had already told us it wasn't just another impact scar. They saw clays, smectites in particular, spread through a fan-shaped delta where two valleys poured in. They traced point bars, inverted channels, polygonal cracking. All of it whispered the same thing. Water once pooled here, and it stuck around long enough to build a complex lake delta system. That's why NASA picked Jezero for Mars 2020. It was the kind of place where you'd expect biosignatures, if Mars ever held them. Perseverance arrived in February 2021, planting itself at Octavia E. Butler Landing. A few weeks later, Ingenuity flew its first hop. From there, the mission unfolded in phases. The rover began in a sandy patch called Crater, scratching into rocks that turned out not to be sediments at all, but coarse-grained igneous cumulates, olivine grains locked in pyroxene. These weren't just dry volcanic leftovers, though. Carbonate and sulfate coatings showed that water had percolated through them after crystallization. Even Jezero's basement was telling a water story. As the rover worked across the crater floor and its margins, it kept confirming this theme: igneous rock, altered and overprinted by multiple paths of aqueous chemistry. But the big prize came in 2022 at the western delta front, the fan front. There, Perseverance drilled into layered sediments, the classic stuff of ancient lakes. Carbonates dominated, with patches of sulfates low in the sequence. That meant calm lake water depositing carbonates, interrupted at times by briny pulses. Life doesn't love brines, but salt is fantastic at pickling organics, locking them away. It was exactly the kind of dual signal astrobiologists dream of. The caveat was sharp, though. Sherlock's fluorescence could be fooled. Signals that looked like organics turned out to sometimes come from exotic cerium-bearing phosphates. No confirmed organics yet, just a set of prime samples cached for return. Then came the newest frontier, the Bright Angel Formation inside Neretva Vallis, explored through 2024 to 2025. Here, Perseverance finally walked into mudstones and conglomerates, full of rounded clasts and fine-grained laminae, light-toned, delicate rocks with veins, nodules, reaction fronts. Near IR told of weak hydration overall, but calcium sulfates, often basanite, were abundant in the nodules. The real surprise was chemical. Sherlock saw Raman bands around 1,600 centimeters to the negative first power, consistent with organic carbon in several mudstone targets. And these organics weren't alone. They sat beside tiny redox features, ferrous iron phosphates, likely vivianite, and iron sulfides, likely greigite. On Earth, both can grow in anoxic lake sediments where microbes are busy reducing iron and sulfate. Vivianite especially is famous for appearing in microbially worked muds. Greigite shows up where sulfate reducers are at play, the kicker. All of this in fine-grained deltaic mud, the faces you'd check first for life. But Mars is a tricky narrator. These minerals can form abiotically. The rover's tools can't tell isotopes from textures at the nanometer scale, so the team calls it what it is. Compelling associations, the strongest yet, but still ambiguous. Only Earth labs, with returned samples, can pin down whether those organics are ancient life or just chemistry mimicking it. That's why sample return looms so large. Perseverance has cached a cross-section of Jezero's history. Igneous cumulates from Crater, altered by water, layered carbonates and sulfates from the fan front delta, and Bright Angel mudstones where organics and redox minerals meet. Together, they're pieces of a puzzle. One tells you about planetary differentiation and timing of water alteration. Another holds the lake sediments that could trap microbial textures. The newest holds the tantalizing chemistry of organics linked to iron and sulfur. When those rocks come back, labs can probe for isotopes of carbon, sulfur, iron, phosphorus, and resolve whether life ever stirred in Jezero's lake. The storyline so far is clear. Jezero hosted a persistent lake delta system, not a flash flood. Water left its mark on both igneous foundations and sedimentary fills. Organics are hinted at, sometimes explained away, sometimes persisting alongside minerals that, on Earth, often owe their existence to microbes. The mudstones of Bright Angel are the high point of that tension. Habitability proven, life still unproven. For now, the verdict is simple. Mars offered the stage, Perseverance has gathered the scripts, but the final reading will be done back home. That's where Sapphire Canyon enters the picture, the most provocative core yet, and the focus of what came next. Vivianite isn't just another mineral to tick off a list. It's a quiet witness to chemical stories that usually don't unfold without life nearby. On Earth, you find it in soft, oxygen-starved places, the bottoms of lakes, wetlands where mud keeps air out, and sediments that still smell faintly of decay. In those settings, microbes are the main actors. They break down organic matter, strip oxygen from iron, shuffle phosphorus around, and in the middle of that activity, crystals of vivianite emerge. Blue-green, sometimes turning darker as they age. Greigite plays a similar role on the sulfur side of the cycle. It's a magnetic iron sulfide, closely related to magnetite and pyrite, but with a character of its own. In many cases, its birth is tied to bacteria that breathe sulfate instead of oxygen, reducing it into sulfide as they chew through organic leftovers. Greigite becomes a byproduct of that microbial metabolism, a mineral trace left behind in the mud. When Perseverance spotted both vivianite and greigite in the same core at Chayava Falls, what scientists now call Sapphire Canyon, it wasn't just chemistry on a page. That pairing, in those specific textures, looked eerily like the kind of work microbes do back home. The rover's cameras and instruments showed off those textures in unsettling clarity. Reaction fronts etched into the mudstone like animal prints, sharp lines where the chemistry flips from one state to another across just millimeters. On Earth, microbes often make those fronts by living right at the boundary between reduced and oxidized iron, or between sulfates and sulfides, carving their territory into the rock. Then there were the speckles, the tiny nodules peppering the surface like black poppy seeds. In terrestrial sediments, microbial colonies or mats can leave behind mineral clumps just like these, little spheres and concentric growths that mark where life once clustered and metabolized. That precision in Jezero's mudstones was enough to raise eyebrows, even among cautious scientists. Timing matters just as much as the minerals themselves. The evidence suggests vivianite and greigite didn't arrive millions of years later from deep fluids or volcanic activity. They seem to have crystallized not long after the sediments were first laid down. That moment in a rock's life, before it hardens completely, but after water has seeped and chemistry has stirred, is exactly when microbes, if they were there, would have been most active. It's also when organic matter is still relatively fresh, preserved before heat or burial could erase it. On Earth, vivianite and greigite often appear within a few thousand years of sediment settling in that early diagenesis stage. To see the Martian rocks hinting at the same kind of window adds another layer of intrigue. Temperature is the other clue. Nothing in the data suggests high heat conditions. No signs of hydrothermal fluids or volcanism dominate the picture. Instead, everything points to low temperature, water-rich chemistry. That matters because high heat tends to wipe biosignatures clean, burning away organics and pushing minerals to form by purely chemical means. Cool, watery mud, on the other hand, is where microbes thrive, where their metabolic fingerprints can linger, locked into crystal lattices or trapped inside nodules. That's why the discovery of vivianite and greigite together under these inferred conditions feels so provocative. It's not just that the minerals are there, it's that they're there in the exact way we'd expect if microbes had once been alive in Jezero's lake. Still, the caution hangs heavy. Vivianite and greigite can appear without life, under the right chemical circumstances. Volcanic gases, slow abiotic redox reactions, or other non-biological processes can also sculpt nodules and reaction fronts. Scientists know better than to confuse a strong resemblance with a smoking gun. That's why they keep calling it a potential biosignature. It's an invitation to investigate, not a final verdict. Perseverance has gathered the samples, but only a lab on Earth can chase down the finer details: carbon isotopes, microscopic textures, organics preserved within the crystals. Those are the kind of measurements that can tilt the balance one way or the other. For now, all that can be said is this: the mineral pairing, the sharp fronts, the nodules, the timing, the cool and watery context, every piece of it lines up with what microbes do here. None of it proves microbes once lived there, but together it paints a picture that feels less like coincidence and more like a possibility waiting to be tested. Sapphire Canyon might just be the closest Mars has ever come to handing us a message in stone. The challenge now is getting that message home, and that's where the debate over Mars sample return takes center stage. The Sapphire Canyon core also sharpens a deeper philosophical question: what counts as proof of life? Planetary scientists are haunted by the lessons of the past. In the 1970s, NASA's Viking landers ran biology experiments that some researchers still argue showed metabolic activity, but without clear isotopic or molecular evidence, the consensus tilted back toward chemistry. More recently, claims of fossil microbes inside Martian meteorite ALH 84001 electrified the world in the 1990s, until later studies showed the features could arise without biology. Each time, the scientific community has pulled back, wary of raising false hopes. That history is why Perseverance's team moves carefully. Minerals like vivianite and greigite are exciting because they so often track with biology on Earth, but the abiotic imposter problem looms. Without isotopes, without compound-specific organics, without textures at the nanoscale, the story stays incomplete. What the rover has delivered is not a eureka moment, but a short list of suspects, a set of conditions where life could have thrived and maybe left fingerprints. That is still extraordinary progress. Jezero's mudstones have taken Mars astrobiology from speculation to testable hypotheses. What happens next depends on whether those tests ever make it back to Earth. That's why Mars sample return has been at the top of the planetary science wish list for decades. With real Martian cores in hand, labs could push the investigation past possibility. They could track isotopic ratios that betray biology, examine textures that look like microfossils, map organics at the molecular level, and pin down the timing of water and climate shifts that shaped Jezero. They could also assess risks and resources for future human missions. It's why Perseverance has been caching its cores with such care. Each one is a sealed promise that the real tests will happen later. But the reality is heavier. The blueprint for sample return involves a lander, a rocket that can lift off from Mars, and an orbiter to bring everything home. It's one of the hardest and most expensive projects ever attempted. Early designs came in around $5 to $7 billion. Recent estimates have pushed toward 10, even 11. That pushes the likely timeline out of the 2030s and closer to 2040. And politics doesn't make it easier. Artemis, Earth Science, and other flagship missions are already stretching budgets thin. The administration's fiscal year 2026 proposal even floated cancelling MSR outright, framing it as too slow and too costly, while promising some vague, cheaper alternative. The House has tried to keep the idea alive. The Senate has yet to show where it stands. Meanwhile, NASA and ESA engineers are sketching stripped-down versions, modular launches, lighter mass budgets, anything to keep the dream alive. Other players, like China's Tianwen-3 mission, are moving toward their own sample return attempts in the same decade. So Jezero's leopard spots sit at the center of a strange crossroads. Scientifically, they're exactly what everyone hoped to find: the right minerals in the right textures, mixed with the right chemistry, in the exact kind of setting where Earth's microbes would flourish. Practically, they're locked away in a capsule on Mars, and whether the world ever learns their true story depends less on geology than on money, policy, and international will. If a streamlined return mission makes it off the drawing board, Sapphire Canyon could finally give a clear answer to the question of Martian life. If not, the best lead yet stays sealed in Jezero's mud, the closest we've come, still out of reach. In the end, Sapphire Canyon is more than just a core of Martian mud. It's a reminder that the universe may be holding secrets just beyond our reach, waiting for patience, persistence, and humility to unlock them. Whether those minerals prove to be traces of life or not, the search itself deepens our story, because in chasing Mars's past, we are also asking who we are, where we came from, and whether we are truly alone.